Welcome to Draw My Life Quantum Theory Edition. Essentially, going to be taking you through a timeline of how I came to be. Max Planck is known as the originator of the quantum theory and is often regarded as the father of quantum mechanics. Following the ultraviolet catastrophe, where it's predicted that the intensity of radiation emitted by an ideal black body at thermal equilibrium should increase exponentially as the wavelength decreases, Planck introduced the concept of quantized energy. He theorized that energy of electromagnetic waves is quantized and actually exists in packets called quanta, as opposed to being continuous. He describes this quantization of energy with his famous equation E equals hv. As the frequency of electromagnetic radiation increases, so does the energy of each quantum. This can be compared to the steps of musical notes or climbing stairs, where values are not continuous but quantized. In 1905, Albert Einstein extended Planck's discoveries regarding quanta and applied them to his own learnings, leading to him theorizing the photoelectric effect. In this theory, when light interacts with metal surfaces, the quantums of light energy, known as photons, would transfer their energy to electrons as they move through the material. This energy transfer allows for the emission of electrons. However, rather than intensity being the dependent variable, as suggested by classical physics, he observed that it was actually specific colors of light triggering the liberation of electrons. Thus, the photoelectric effect proposes that when triggered by light, the emission of electrons from a metal surface is dependent on the frequency or color of the light energy rather than intensity. Moving on to Niels Bohr. His first contributions to quantum physics began in 1913 during postdoctoral research with Ernest Rutherford. Prior experiments had revealed that the atom structure consists of a positively charged nucleus with lighter negatively charged electrons surrounding it. Classical physics found flaws in the structure, believing it to be unstable. This led to Bohr reasoning that if light energy is quantized, then electrons' energy levels should be quantized as well. He theorized that electrons occupy or orbit the nucleus in specific energy states. This quantization allowed Bohr to propose that when hydrogen atoms undergo energy changes, such as heat or electricity, they emit photons as electrons transition between these energy states, emitting light at specific wavelengths. In 1922, Arthur Compton, applying Einstein's theories to his own discoveries, aimed to address a phenomenon that conflicted with classical physics. He observed that when high-frequency X-rays collided with low atomic weight elements, the X-rays' wavelengths notably lengthened post-collision. Compton proposed that X-rays consist of photons, and that during collisions with electrons, these photons transferred energy, resulting in longer wavelengths. His findings provided support for the emerging quantum theory. It demonstrated that electromagnetic radiation, in this case X-ray rays, exhibited a dual nature of acting as both a particle and wave, as well as a transfer of energy during collisions with atoms. In 1924, Louis de Broglie proposed the concept of electron waves, where, similar to light, matter, specifically electrons, also have a wave-particle duality where they exhibit both wave and particle characteristics. By applying Einstein's work and his own reasoning, he concluded that if light waves could act as particles, as seen in the photoelectric effect, then particles like electrons could behave as waves. Calculations regarding electron motion within an atom indicated that electrons are limited to orbiting around the nucleus. These concepts resolve the confusion of why electrons follow specific paths in an atom, as their wave-like nature is constrained within atomic boundaries, preventing interference with itself outside these boundaries. In 1926, Erwin Schrödinger built upon Louis de Broglie's theories, applying wave theory to electrons to develop a wave equation that calculates the probability of an electron's location within an orbital at a given time. His wave equation describes the wave-particle duality of electrons, resulting in a function denoted by three quantum numbers: the principal quantum n, the orbital-shaped quantum number L, and the magnetic quantum number ml. An electron can be viewed as a stationary wave, with its energy being quantized because it can only possess specific wavelengths. The model depicts the nucleus surrounded by an electron cloud and introduces the concept of sub-energy levels within electron orbitals. Also, in 1926, Max Born used Schrödinger's wave equation, as well as Heisenberg's observations of particle properties like position, momentum, and energy, to advance our understanding of electron positions. He classified particle characteristics into mathematical matrices, equating them to the Schrödinger wave equation. He devised a method to calculate the probability of a particle's presence at a particular location upon measurement or observation, but not its exact location. When a particle interacts with a potential and scatters, the wave function at that specific time and location reflects the likelihood of finding the particle in that particular area at that particular moment. In 1927, Werner Heisenberg introduced the uncertainty principle, which limits the simultaneous measurement of both the position and velocity of an electron. He theorized that there is a fundamental relationship between momentum and position uncertainties, making it impossible to know both values with absolute certainty. According to the principle, the more accurately one measures either position or momentum, the less certain they become about the measurement of the other. Heisenberg's principle allows us to predict the probability of finding an electron's position within a specific area, rather than determining its exact position and velocity simultaneously. Last, but certainly not least, Erwin Schrödinger's cat in 1935. Schrödinger's cat was a thought experiment illustrating potential misinterpretations of quantum theory. The experiment involves placing a cat in a sealed box with radioactive material and poison. If the radioactive substance decays, it releases poison, potentially killing the cat. However, until the box is opened and observed, the cat is considered both alive and dead. This experiment highlights the paradox of quantum superposition, where outcomes are uncertain until observed, leading to dual states of possibility.